Good afternoon, everyone. Hope you can hear me. Okay, my name is Priya, and I'm going to talk about voice over LTE and voice over Wi-Fi calls today. As I said, my name is Priya, and I work at ERNW GmbH. ERNW. It's a company in Germany. I like to do telecommunication security, also some binaries. I like to play with PCAPs, logs, and I like a little bit of everything in security. I have a blog. It's kind of outdated, but I also write in company blog, Insinuator. So today we'll be talking about, as I said, about voice over LTE and voice over Wi-Fi security. I will give a very brief introduction and a background about the structure of the systems involved, and also some attacks on OpenIMS, which is an open source implementation of the IMS, or IP multimedia subsystem, which is the backend of VoLTE or voice over Wi-Fi. So that's more like a simulation attacks because it's not the real provider. But after that, I will be also trying to see how we can apply these kind of attacks in real telecom providers, and also proposing some mitigation. So to start with, voice over LTE or voice over Wi-Fi are variants of voice over IP. This means, apart from the traditional circuit switched networks, these technologies are using packet switching, or in other words, the data is transmitted as packets like in the usual internet, like IP packets. And the backend is called IMS, or IP Multimedia Subsystem, which handles all the calling and all the IP-related functionalities. And it came for the first time, voice over LTE came in South Korea by SK Telecom and LG. And in Germany, it came only in 2015, March, by Vodafone. And voice over Wi-Fi came only in 2016. So this means this is rather new and not widely used. But I'm pretty sure that most of you already have voice over Wi-Fi. Or in other words, it's called Wi-Fi calling in your phones. And also voice over LTE. So if you make a call and if you don't see the LTE switching back, then most probably you are making the call via LTE or using VoLTE. But most of the phones like Samsung, iPhone, or Sony Xperia support this features. So to start with, I will talk a little bit about the IMS background, or IMS, or IP Multimedia Subsystem. So that is the VoLTE stack. That's the user interface and the tower and the gateway and the IMS. But in my talk, I'll be covering only these three layers, so which is the IP and the layer above. So it's more like an application layer talk. Nothing at the radio or the physical layer. So it's only going to be about IP or voice over IP, which is, we will talk about that later. And these are the systems involved in the IMS. So IMS consists of call session control functions, so CSCF, and these are the systems that actually provide the calling capability. And there is a gateway, and there is also HSS, which contains all the identification information or authentication information, or like your IMSIs or information like that. This is how a calling would look like when Alice is calling Bob. The first packet that gets sent is called invite. I should talk about SIP. SIP is Session Initiation Protocol, which is the protocol which is very similar to HTTP, which is a text-based protocol. And when you make a phone call or voice over LTE call or voice over Wi-Fi call, there is a SIP packet that can get sent via the IP interface. And yeah, it goes to your provider, so it could be anything there. And then, yeah, it returns ringing. That's when you hear the ringing bell. And yeah, when the person picks up the call, then there is a 200 OK message sent back. And it is at this region, it's usually RTP, where the real voice call happens. And yeah, that's when you get charged for your call and so on. So to look a little bit deeper, that's how the SIP would look like. So as I said, it's similar to an HTTP protocol. So instead of the get and post, you have invite or register or options or keywords like that. Then you see from and to address. So this is actually a voice over IP example, but in case of voice over LTE, this will be a phone number here and also the to phone number. Then you also have something called SDP, which is Session Description Protocol. But the details are not so important at the moment because they agree on what kind of support does your phone have and how are you going to make the call and so on. But we are mostly going to play with the SIP part for today. So so the first part is going to be about attacking OpenIMS. As I said before, OpenIMS is an open source implementation of the IMS, which contains the call session control functions implemented in that. So there are some requirements for this. I used SIP proxy as a tool, which allows to basically proxy and do the injection and play with it. You can also use VoProi toolkit. So they already have some exploits in Metasploit. So if you are playing with Skype or something like that and want to try, you can use VoProi. In this test, I'm using mainly IMS clients, like it's Twinkle in Ubuntu or Boghe in IMS or in Windows. But as I said before, this is kind of simulated attacks as it is in a simulated environment, and I have my own VM as the backend. So that's how the SIP proxy tool would look like. You can set up the client and the port, and and that's the OpenIMS implementation. So it has got the call session control function systems and the HSS as its parts. And how is it related to voice over LTE and voice over Wi-Fi? So as I said, it makes use of SIP or Session Initiation Protocol, which is very same as in the case of voice over IP. And we are mainly going to do some SIP header injections in the first phase. And also another important thing to note here is that there is no IPsec in this simulated attack environment scenario. And both attacker and the other end user are registered users. Sorry about the grammar. So the first attack is MSRP fuzzing. So MSRP is message session relay. So whenever you send a chat message to keep track of the relay, this particular protocol is used. But that's not so important. So there's a particular header, and if you give a first input into this particular header, giving a long string, so that's an attack which is already there in the VoProi Metasploit toolkit. So you can simply use the exploit and try to test this. And you will find that it basically crashes the client on the other end. So you are making a call to someone, and you can crash the other end user if they're using a bad client, of course. So that was the first attack, which basically tries to do some fuzzing on the header. So that's the first attack which I wanted to talk. The second attack is related to location manipulation. So in the SIP header, there is a particular header called p-access network info. This basically defines which location are you in. So yeah, it contains these informations, which is mobile network code, mobile country code, local area code, and cell identifier. So these are integers, but this basically maps you to which exact location are you in right now. So your phone, when making a SIP call, contains this p-access network info, and an attacker can simply change this and put whatever value he or she needs. And this is not checked in the backend in case of OpenIMS. So as we see, when a modified p-access network info is sent, it is accepted by the IMS and forwarded to the other end. And there is no cross-validation with HSS, which is the backend data server, and for user location, which is used during initial registration of the phone. And this can be used for evading lawful interception techniques. Another interesting attack is roaming information. So there is another header called p-visited network ID. So this header field is not supposed to be coming from the user end. It is added only at the access point layer. But if an attacker tries to put this header already from the user end, inject this header, we found that at the OpenIMS side, on the other side, the fake domain is not removed, but instead just the original one is added in the later. So, well, basically, it also depends how the charging functionalities of a particular provider is implemented. But if it's not implemented properly, an attacker can make use of making his roaming calls as local calls just by changing, this header values. And then SIP is also an extensible protocol, so you can add additional headers. So, the additional header can be added as X header, and you can try to send whatever content you want, and this still get accepted, but at the server side and gets forwarded to the other end. So, this is an extra header, and you could simply send that. So in the first phase, we did some simulation attacks with OpenIMS as our backend, as we saw, there was a fuzzing attack, there was a user location manipulation, there was another roaming information manipulation, or trying to put extra header injection. So to understand this is more like a man-in-the-end attack. So the user, a registered user itself, is the attacker in that end. And all these attacks were done without IPsec. These are not the only attacks. There are more obvious attacks possible, like spoofing, injection. So if there are XML entities used, XML or SQL, or trying denial of service, or fuzzing, as we saw. So these are the kind of attacks which is already there in the voice over IP field, or in this area. Now we are trying to see how what is the current state, and how can I use this knowledge for attacking the telecom providers. In this case, it was not as easy to do injection attacks, but because there is IPsec in place. So, and you don't have the keys for the IPsec. So, in case of real providers, that is the first target for me. If I want to do some sniffing or injection, I need to get the IPsec keys. So in this testing, had voice over LTE or voice over Wi-Fi enabled SIM cards. So not all SIM cards support that. So first of all, you need to have supported SIM. And I also used SIM trace hardware. This is by Osmocom and not Osmocom, I forgot. Yeah, but it's an interesting hardware device that allows you to sniff the interface between the SIM and your phone. That is how I'm going to extract the IPsec keys. And then you also need voice over LTE or voice over Wi-Fi enabled phones. And yes, there is IPsec here. There is going to be ESP or Encapsulation Security Protocol, which is a part of IPsec. So if you want to play around with it, you need to compile Wireshark on your own with gcrypt library enabled so that you have more additional features. So yeah, to start with, the interfaces which I'm looking at are generally called RMNet 0 or RMNet 1. This simply contains IP addresses just like your Ethernet interface. And in case of voice over Wi-Fi, there is a tunnel which is going to be sent through WLAN 0. But I also found another interface called EPDG1, which was there as a virtual interface, which contained all the data which I could use for sniffing. And then I also did iSIM interface with the SIM trace hardware. So we will get into details of all these in detail. Also, as I told before, there is IPsec in place here. So there is ESP, which is Encapsulation Security Protocol, which is used. So it's not plain as in the case of OpenIMS before. And yeah, this means that there is integrity protection. So there is always a hash added to each and every SIP request that gets sent. And in case of voice over Wi-Fi, there is encryption, of course, because yeah, it's going through the internet. So so this is how the ESP packets would look like. And yeah, in case of voice over LTE, it's always IPv6. In case of the providers which I looked at. So for testing voice over LTE, the specific interfaces are called RMNet 1, 0, 2, 3, as such, but these are the main interfaces to look into. One is usually for your data. So your LTE data, mobile data works through one of that, and one is for voice. So when you enable voice over LTE, the other new interface gets turned on. And for voice over Wi-Fi, I could look into these. But WLAN 0 always had encrypted communication in this case. But this particular interface had non-encrypted traffic. This is simply using ADB shell and ADB forward for viewing the traffic. So as I said before, to give a clear idea, in case of voice over LTE, there is no encryption, but only integrity protection. And the traffic is sent, and we are listening at RMNet 1 or RMNet 0. It changed according to providers what exactly is the interface name. And in case of voice over Wi-Fi sniffing, there is an IPsec tunnel here between WLAN 0, but there was additional hidden interface called EPDG, which contained all the data in a non-encrypted form, which we could look into. I don't want to discuss in detail about this, but if somebody is interested, this could be very useful, especially in the setup, because routing is disabled in the voice over LTE interface, so you can't simply set a route table for that. So there is a trick to use IP tables to do that. That's basically sending to man in the middle, which is my laptop, and then for routing it back to the phone. But in some cases, I didn't have to do this as well. Sometimes it works with SOCAT and burp and just trying to inject. But I have a demo in that case. Yeah, we will take a look into that. So what did I find when I was trying to look into the interfaces which I mentioned before? I found information disclosures. So there was IMEI numbers, which I could see of the caller and the callee. So IMEI is the private identity of your phone, like a serial number of the hardware MAC address kind of thing. Yeah, and I could see uTranscell ID, but I could see this only in the SIP register. So this is something which is sent before the whole IPsec begins. And yeah, if there is something like a fake base station or something, yeah, that can lead to leaking of this. But there were other cases where we were able to see the location information of a caller getting leaked at the callee side, which is bad. But yeah, I just rechecked this yesterday, but that is not there right now. So yeah. Yeah, at the callee end, yeah, there is still IMEI numbers. And this is the worst part, that it also leaks the IMSI. IMSI is the private identity of your SIM card. So your SIM card has a public identity, which is your phone number, and a private identity, which is used for authentication at the back end. And yeah, leaking that is not so good, and it's bad. So that was a finding. And there were some private IPs of the IMS, but that's not of high security implication, as I see. So we have some information disclosures, but I wanted to see how I can get the IPsec keys, and so that I can do some kind of injection, because yeah, there is integrity protection in each and every SIP packet that gets sent. So if I want to inject something, then I have to generate my own hash of the packet. So I use SimTrace, and this is how it would. So it will basically listen at the interface in the SIM. It's called the iSIM interface, and gives you, yeah, a payload of whatever it sees, just like that. Yeah, we kind of broke that device, and that was with S7, but it's much more easier with Samsung S6. So you just take out the SIM and put that in this hardware, and then connect the yeah, SIM tracer into the SIM slot of the phone. And then you connect the SIM tracer to your laptop. So that's the setup. Okay. Now I need to say a little bit about EAP, aka this is Extended Authentication or Key Agreement Protocol. So this is the main protocol which is used for authenticating your SIM card with your provider. And how this works is the server would send you a challenge, a random challenge, and also, so that's called the RAND, and also an authentication value of the server to you. And the peer or the user end, based on the challenge, which is the RAND that is sent, it generates a response, which is the RES. And it also generates the session key. And that's the interesting point for us. Okay, so the session key consists of CK and IK, which is ciphering key and integrity key. And that's what we are going to look at. With the SIM tracer hardware dump, which we got before, when I put that in Wireshark, I could dump that as a PCAP and try to put that in Wireshark. I see that, sorry. Yeah, I see that as GSM algorithm and authenticate and a get response packet right there. And I was able to see the rand and authentication values and also the IK and CK in there. But it was not parsed properly, so Wireshark couldn't read it. So I had to check up the specifications, and I wrote a Wireshark dissector myself to get the CK and IK out of that. And I also wanted to check if this itself is the key which is used in sending the ESP packets, which we actually see in the RMNet or WLAN or EPDG interfaces, which I was talking about before. So when you give a wrong key, it would tell you it's incorrect, and I just need to set up SA or security association and give them what is the algorithm, and this is the key which I extracted. So this is for authentication, so this is the IK part, and I provided that it's the authentication. And I was able to see that Wireshark detected that this is the right key which is used. To give a summary, we saw that we tried to sniff at the different interfaces of VoLTE and voice over Wi-Fi, and we found information leaks like IMEI and IMSI and private IPs. And then we tried to look at the ISIM interface, and then wrote a Wireshark parser and got the IK and CK. We also did the validation with the Wireshark gcrypt library to see if this key is itself used. Overall we had some attacks in OpenIMS, and also looked at current providers and what they have. This is what we discussed right now, that we extracted the CK and IK. Maybe I'll show a demo right now, which is... so with ADB shell, I'm trying to get a shell in my phone. It's a rooted phone. And that is the interface, RMNet 0, how you see that. So in case of voice over Wi-Fi, you will also see EPDG1 and also RMNet 1 and more of those. I'm simply trying to do TCP dump, and with ADB forward, you can just give that command in your shell on your desktop and get all the packets. Now we want to see only SIP. We see some SIP packets already coming there. Now at this point, I am sending a message from my phone. So you can also make a call, and that will also be there. Now we see the SIP invite packets. And then you can see that your phone number and... this is how it looks like. That's your location information. Yes, that's also the server response in blue. And that's the message which I sent in my phone. Now I'm trying to do a simple replay attack by trying to send that by a burp. Yeah, just changing the content. And I haven't tried a lot of injection in this right now, but and I'm sending that to the phone, to the Wi-Fi interface, as my laptop and my phone is in the same Wi-Fi network. And I open a SOCAT listener, which will listen to my packets coming from burp. Now, this is the most simplest setup, but this may not work like this always. Sometimes you have to use IP tables, like the list of rules, and do post-forwarding and pre-routing. But in this case, this is easier. Initially, when I tried to inject, I couldn't, because there were some values which I had to change to make that as a unique message. Because there are values like this branch and call ID and tag and values like that. I'm just changing that later. To another random value so that it appears unique. After that, when I try to inject that again, then I got a successful response from the server. So the message basically got sent and it got accepted on the other side. That's it. So it's easy to do more of injection attacks in the same setup. So I just showed only the setup, and you can try injection in all the other headers and try to see if it works or not. So the mitigation for these kind of injection attacks towards the IMS server, the first basic policy is never trust the user end. So never assume that having IPsec will solve all the problem of injection, because it's easy to get the IPsec keys and do injection attacks. So there should always be something like traffic monitoring in the gateways, and that performs deep packet inspection, and also whitelist rules to see what is expected in each header fields in SIP, and also encryption, at least to prevent something like a fake base station to see your IMSIs, and also user awareness to not connect to suspicious providers that pops up in your so that's it. If you have any questions, we can discuss that now.
Okay, thanks very much, Priya. So, any questions? Okay, people taking lots of photos of the stuff there. Any questions in the room? Okay, everybody wants to get to the donuts, I can see. Hackers donuts. Who ordered those things? Okay, well, Priya's here, and I'm sure she'll be very happy to talk to you guys, talk to everybody outside if necessary. So, get the donuts.